very, very short period of time where this is occurring.
Okay, so you didn't hold on to it quite that long.
Yeah, it's really hard to hold on to twice the pressure of the sun for very long. That's about 400 to 500 billion atmospheres. So it's nothing lasts that long.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues.
Produced by Soapbox Media.
Hello and welcome to another episode of The Rational View. In this episode, I'm going to start a new series to explore another interesting scientific topic that has recently made a big splash in the media: nuclear fusion. For decades, the promise of nuclear fusion has been held out by scientists as the ultimate in clean energy sources. The same energy as the sun, with no transuranic radioactive waste stream, just fusing hydrogen protons together to make helium and boundless energy. The problem is that it's very difficult to simulate the conditions of the core of the sun on the surface of the Earth. And this is what's been hindering scientists for so long. Even in the core of the sun, where temperatures are measured in millions of degrees and the pressure is higher than anywhere in the solar system, fusion is not a fast or efficient process. I mean, I guess that's good for us. If it were efficient and fast, the sun would just rapidly burn out in a huge supernova and we'd all be dead. As it is, the sun will happily burn hydrogen for about 10 billion years before it starts running short. So a random proton in the surface or in the core of the sun is going to happily bounce around at millions of degrees and high pressure for billions of years before it ever takes part in a fusion reaction. It's this challenge that researchers on Earth are faced with to make efficient fusion energy in a room temperature lab for the past 50 years without much success. So today I'm going to be interviewing a team of researchers who are working on trying to crack this problem to find out just how close we are to practical fusion. If you like what you're hearing, please press like on your podcast app. Show me what you like. Give me your comments. Love to hear from you. Come chat with me on our Facebook group, The Rational View. Omar Hurricane is a distinguished member of the technical staff at Lawrence Livermore National Laboratories. Omar received a PhD in physics from UCLA in 1994, staying on as a postdoc until 98. Omar is a designer at Lawrence Livermore National Labs, working on topics of stockpile stewardship and high energy density physics. He became the chief scientist for the Inertial Confinement Fusion program. In 2009, Omar was awarded the U.S. Department of Energy Ernest Orlando Lawrence Award for National Security and Non-Proliferation. Omar became a fellow of the American Physical Society Division of Plasma Physics in 2016, and in 2021 was awarded the Edward Teller Award and medal from the American Nuclear Society for leading efforts to obtain fuel gain, alpha heating, and a burning plasma in the laboratory. Omar, welcome to The Rational View.
Thank you for inviting me.
Omar, can you tell us briefly about your role in the nuclear fusion experiments at LNL?
Well, so I'm technically chief scientist for the program, but my particular role in the case of the experiments from the recent publications is that I developed the concept that we're following, which we call the hybrid concept, several years ago as a tactic or strategy to attempt to get us to ignition, along with my colleagues, Debbie Callahan, who's not on the call today, Alex Zylstra, who is on our call today, who's the lead experimentalist, and Annie Kreitcher, who is the lead designer for the experiments, along with a large team of people who work in the Inertial Confinement Fusion program at Livermore and on the National Ignition Facility.
Okay. Dr. Alex Zylstra, will go to you now, received his bachelor's degree from Pomona College in 2009 and his PhD in plasma physics from MIT in 2015. From there, he joined the Los Alamos National Laboratory as a Raines Distinguished Postdoctoral Fellow, working on developing novel inertial fusion concepts. He joined LLNL in 2018 as the experimental lead for the Hybrid E campaign, which subsequently produced the first laboratory burning and ignited plasmas. Alex, welcome to the Rational View.
Thanks. Happy to be here, Al.
Can you tell me a little bit about your role in the nuclear fusion work?
Yeah, so Omar and I are both, like you said, on the scientific or physics side of the team. It's, of course, very multidisciplinary, many teams working together. And so within that physics team, then I was responsible for leading the experiments that developed this particular design that we're talking about that produced the record shot last August. So that basically is a series of experiments we conducted over the past 4 years or so to get to where we are.
So just to get a framing for this, how big is the group that's working on this experiment? And this is called the Hybrid E concept that's currently going on. Is this the main work that's being done there?
Yeah, so Hybrid E, it's, well, first of all, we have to apologize for the jargon. It's basically an internal name that now we use talking to you. That's basically one kind of particular what we call design, so a concept for a target, laser pulse, and so on. Of course, we've gone through many of those over the years. We can talk through the whole history. And so the development of that particular concept was a kind of a core group of people. But then to actually execute the experiments on the facility is a much larger group of people. And the whole community is well over 1,000, as you can see on the recent publication that our team put out is, I think, 1,200 people or something. Omar probably remembers.
1,351.
There you go.
Although, that includes people who worked many years ago and have now retired and so forth, because it took over a decade to build the machine that we're working on, and decades of work leading up to where we are now. So many generations of people were involved.
Yeah, indeed, and that's of interest, I think, to look at the background and how far we've come. What's your annual budget on this program? This is huge. 1,000 people, 1,300 people.
I only know the numbers approximately, but I think the annual budget for the National Ignition Facility at our laboratory in Livermore, which is Lawrence Livermore National Lab, is on the order of $350 million per year to run the facility. That fluctuates depending on budgets from year to year. And that's been going on for, over a decade, maybe a couple of decades of that level of funding. Again, I don't know exactly. And then the ICF program, and ICF stands for Inertial Confinement Fusion, which is the scientific program that Alex and I and our colleagues belong to. I think the budget for that is on the order of $60 million a year, roughly speaking. So it's a fair chunk of change.
Yeah, wow. So Alex, could you tell me a little bit about your group's approach to achieve nuclear fusion? How does your system work, and how long have you been at it?
Yeah, so like Omar just mentioned, we pursue what's called inertial confinement fusion. There's actually a number of ways that people go about that. At Livermore, the approach that we pursue uses lasers as a driver. So basically, inertial fusion, one way to think about it, if I back up for a second, for fusion, we need to get the fuel to have a high product of the pressure and something we call the energy confinement time, which is sort of how long it sits around hot. And so inertial fusion, we go to very high pressures, higher than the center of the sun for our approach, and in very short times. And so the way that we do that is you have to use a very energetic driver. In our case, that's a laser. So the National Ignition Facility is it's the largest laser facility in the world. Physically, it's about 3 football fields. Most of that is just the laser itself. And all of that laser energy, we concentrate onto a small target. It's about a centimeter in size, the total target. The first part of the process is that the lasers go into what we call a hologram, which essentially converts them into X-rays. And those X-rays are then used to heat and compress a capsule that actually contains the fuel. And so that the compression of the fuel inside that capsule puts it at those extreme conditions, again, higher pressures and temperatures than the center of the sun.
Wow. So you're turning laser light into X-rays with this holon. Why do you need to use X-rays? What's the advantage of, it's photons?
That's a great question. And like Omar mentioned, people have been talking and debating that for decades, literally decades. Basically, there's pros and cons to each approach. So there are people that pursue what we call direct drive, where you use the lasers to directly illuminate the capsule containing the fuel. And basically, the advantages of X-rays are in as we try to compress the fuel, there's a number of hydrodynamic processes that can mix up material. And so the X-ray drive is a little bit better for that process. Omar actually could probably explain that even better than I can.
Yeah, well, it's the laser energy basically when it hits a material, it can ionize it, and when the material ionizes, electrons are liberated, and that can generate pressure, and it also tends to generate X-rays. So our chosen approach of indirect drive, you shoot the lasers into this metal can, which is the holon, and it converts the laser energy into X-rays, and that creates a smooth bath of radiation around the outside of the capsule. The X-rays penetrate into the surface of the capsule just a bit and cause the outer surface to explode, and that generates a very high pressure on the order of 1 to 200 million atmospheres of pressure that accelerates it to very high velocities. And I'm talking about velocities on the order of 300 to 400 kilometers per second, which is about 20 times faster than the fastest projectiles that you might be able to fire out of, high performance rifles and things that we have here on Earth. That accelerates that shell of material inwards upon itself, and it's basically a spherical configuration that we're illuminating from the outside, and that causes the fusion fuel that's inside that capsule to get squeezed up to very high densities and very high pressures, like Alex was just mentioning. At some point, as this spherical configuration is coming inwards upon itself, that's called an implosion. It runs out of a place to go, because it's all centrally directed. And when it runs out of a place to go, the kinetic energy that it acquired as it's screaming inwards at high velocity turns into internal energy, and that's where we get the pressures and temperatures. And for a moment, you get these pressures that are more than twice the pressure at the center of the sun. The fusion reactions become very copious, and they start to create more heating internally than we put in externally, and that overcomes all the losses that Mother Nature throws at that plasma to try to cool it off, and that causes an exponential or very rapid increase in temperature for a brief moment, and then the thing just blows itself apart. And in our case, we've been working at this for years. We finally got to a state where the heating inside that plasma that we can hold on to momentarily far exceeds all of the losses that tend to take the heat away, and that particular state is called ignition, and so that's what we've done recently.
That's the paper that you recently published, and it's got a lot of media attention. The first attainment of ignition in nuclear fusion, effectively. Is this in any nuclear fusion process on Earth the first attainment of what you call ignition, or is that even a thing that happens?
It's the first attainment in the laboratory.
Right.
It's the first attainment a controlled way in a laboratory. Yes. So, and that's exciting because a lot of people have been working in this for like many decades across the planet. So,
so when your fuel is giving you back more energy than you're putting into the fuel, you now have ignition. This is the first time it's happened in a controlled fusion reaction. So is this something that the tokamak people, the ITAR people are also trying to do, and they've yet to succeed in that? Is that the correct understanding?
Yeah, well, yeah, there are a variety of different ways to get towards ignition using different fusion devices, and magnetic fusion is one approach. Again, that people have been working on for several decades, and they're making steady progress. Just as much as we are. But in this case, we are the first ones to get to this condition that we call the Lawson condition, where that heat balance is finally kind of going in the favor of giving one ignition. So I don't think they're far behind, though.
What did you guys have to do? What was the breakthrough that achieved ignition? What technical wizardry did you guys apply to make this happen?
If we go back, we've been trying to do this for many years, and what happens when you try to generate these high pressures and temperatures and try to hold on to it for a certain amount of time, Mother Nature doesn't really like putting a lot of energy in a small volume, so she throws physical processes at you that try to cool the plasma off and try to smooth out gradients, and we call those physical processes instabilities. So a lot of what we've been doing over the last decade is trying to mitigate these instabilities through design changes. One of the other issues that we have in our particular technique is controlling the symmetry of that implosion to try to get an efficient conversion of the kinetic energy into internal energy, which doesn't happen if it's very asymmetric. So we've had to learn how to control the symmetry better. And so there have been a number of challenges that we've encountered over the past decade. And we've had to basically address them one by one with first understanding what the challenge was and then testing out mitigations through changes to the design, through improvements to the target, and so forth. Alex, do you want to add to that?
Yeah, the other thing I would add is that our approach to fusion is actually very inefficient at coupling the laser energy into the fuel. So the conversion to X-rays is actually pretty good. It's about 90% or something, but only about 10% of the energy is actually absorbed by the capsule that contains the fuel. And actually most of that is wasted in the sense that it doesn't go into the heating of the fuel itself. Only about 1% of the laser energy actually goes into heating the fuel. And so, people obviously have recognized this. And, one of the key things that we did in the development of this recent design is to improve that efficiency while not making other sacrifices. So it's such an integrated problem. It's actually relatively straightforward to improve the efficiency if you sacrifice something else. But the thing that's really challenging to do is improve the efficiency and not sacrifice anything else. And even there, I make it sound like one thing, but it took us a few years to figure out how to do that actually and implement it in practice.
Wow. So you mentioned symmetry. To obviously, you're squeezing something to higher pressure than the surface of the sun. How many beams do you need to get the sort of symmetry that you need to achieve?
So NIF is 192 laser beams,
192.
which sounds
Wow.
Which sounds like a lot, but actually, like Omar said earlier, one of the big advantages of using the HOLROM is that it helps smooth some of that out. And so the radiation field inside the HOLROM, if we control for some of the geometric effects and so on, can in theory be quite smooth. So it's a big challenge. I think one way to think about it is it's kind of an analogy is the change in volume of the capsule that we need to achieve is about taking something the size of a basketball and compressing it to the size of a pea. So that sort of gives you a sense for the change in volume. And if you don't do that correctly, it's like trying to squeeze a water balloon in your hands, right? It'll poke out wherever you're not pushing on it.
So you've got 192 beams coming in. And what's the pulse duration? How long is the laser pulse? I mean, you're trying to push the energy density really high. So obviously you got very short pulses. So how short is the pulse that you have to synchronize here?
It's about 8 or 9 nanoseconds, so billionths of a second.
Okay. And how long did you have energy coming out of this fuel? What's the duration that you created energy for?
The burn duration is about 100 picoseconds, so trillionths of a second. Very, very short period of time where this is occurring.
Okay, so you didn't hold on to it quite that long.
Yeah, it's really hard to hold on to twice the pressure of the sun for very long. Yeah, that's about 4 to 500 billion atmospheres. So it's nothing lasts that long.
Well, obviously, you need that higher pressure because the fusion, even in the core of the sun, is not that efficient. If it were, the sun would go supernova and we'd all be dead. Uh, so you really need to jack it up to get useful energy out of there. What is the fuel that you're using for this experiment?
Yeah, so we use deuterium and tritium, which are two isotopes of hydrogen. So actually, since you just mentioned the center of the sun, go on a little bit of an explanation. The sun undergoes something called PP fusion. So normal hydrogen, you take two of those, putting them together eventually to make helium. It actually is an extremely low energy density, the fusion that's happening in the sun. I think the heat production is actually less than what you get in your body from chemical metabolism, like per volume. DT is many, many orders of magnitude easier fusion reaction, which is why we pursue it in the laboratory, because it's got the highest cross section. Even though it's taken us so long to get to this point of ignition, DT is the easiest fusion reaction to get to that point, which is why we've been pursuing it.
And just to interject, DT, those are isotopes of hydrogen. It's deuterium and tritium. So
those are frozen in a ball?
Not in a ball. That's actually the DT fuel is actually frozen in a layer on the inside of that shell, the capsule that we talked about earlier. And the reason why it has to be a shell is because we have to accelerate this thing inwards upon itself and then have it crash into. It's almost like taking two cars and driving two cars straight at each other and banging them into each other. And when they bang into each other, that's when we get the conditions we need. If it was full of fuel, we could never accelerate to the high velocity that we need to achieve to get the pressures and temperatures that are required. So there's a team of people, our cryo engineers, who actually make that DT layer on the inside of our capsule for every experiment, and it's quite actually a lot of work and an interesting science in itself.
Yeah, I can imagine. I mean, hydrogen is not something that liquefies easily or freezes easily. I guess deuterium and tritium might be a little bit easier. So you've got this expensive whole room and a huge expensive laser, and you've achieved ignition now with this system. What are the next steps? What are you guys working on next to improve this system and get it closer to practical?
That's a great question. What was nice about the recent work is it's basically an existence proof that we can get ignition and this is possible. And that wasn't guaranteed. And there were a lot of people who were skeptical that it was ever going to be possible for us or anyone else in the world working on fusion. So that's kind of behind us now. What we'd like to do is push the robustness of our platform so that we can get that action to happen repeatedly. And we're learning what we need to do in order to accomplish that. And we'd like to push the performance of our fusion implosion to higher levels so we get more fusion yield out. And it's going to take us a bit of work to kind of get to the stage where we're getting so much more energy out that it starts to look more favorable for practical uses and starts to rival the amount of energy that the laser consumes to do the experiments in the first place. So that there are a number of tactics that we'll be pursuing along those lines in the upcoming years, and most of them just involve changes, relatively evolutionary changes to the design of the capsule, the laser pulse that we shoot at the hull ROM, and changes to the hull ROM itself.
I think just to add a little bit to that too. I think it's important to remember that the NIF is an experimental facility, right? So our primary goal is advancing the science and understanding of this, and it's actually in particular the science and understanding that's relevant to the nuclear weapons mission. That's our primary sponsor. One of the things that's generating a lot of interest now is potential energy applications because you make a power plant out of this stuff. And so just to kind of throw out some numbers, as an experimental facility, we do maybe 10, 20 of these full ignition experiments a year. NIF does a lot of other experiments, but these ignition experiments, it's sort of 10 or 20 a year. A reactor would have to do about 10 a second. And as Omar was saying, we still haven't quite gotten to the point where the fusion output is even equal to the laser energy. And for a reactor, it would need to be much greater than the laser energy. And so those are some pretty major challenges, but people are starting to think about that more seriously now that we've gotten to this scientific point.
So for a practical future reactor, you would have to be dropping a hohlraum into the beam focus at a rate of about 10, 20 hertz and firing your 192 beams at that rate to get the energy out. From a practical sense, keeping a lot of high power lasers running properly without blowing up your optics seems like a real challenge. I've worked with lasers in the past, and they're not up 90% of the time.
Yeah.
What's how much of your time is just maintenance on the optics?
On NIF, it's extreme. I mean, again, there's an entire team of laser scientists who are always trying to improve the laser, and another entire team of people who just keep the facility operating. So, I mean, it's an enormously complicated machine to keep operating, even at the level that we shoot it at now. On the other hand, I think there are analogies that people like to make to industry. And so one of them is for like EUV lithography for computer chips. It turns out that the system behind that actually has some similarities to these sorts of things where you're shooting targets in and hitting it with a laser at a very high repetition rate. And there are commercial systems now for those that are running very high repetition rates reliably for years. And so I don't think it's impossible, but it is an extreme technical challenge. And I think it's important not to lose sight of that this is not something that is easy to do for sure. Even once all the science is worked out, actually building a plant is, one of the most, if not the most, intense engineering challenges that we've tried to undertake.
And just for reference, EUV lithography is extreme ultraviolet lithography. This is used to make all of the microchips in your computers. They fire ultraviolet lasers because the short wavelength, you can get really good focus on these photons, and you can get tiny features, so you can get billions of transistors onto a single chip. And so the lasers there are comparable in challenge to what you guys are working on, and it is a process that's been industrialized, maybe only at a couple places in the world, but it has happened, and it's worthwhile. And obviously the goal at the end of this, if we can get practical fusion giving back energy, obviously the hope, I guess, is similar. Could you maybe just let's talk a little bit more about what a practical fusion reactor of the future might look like. Is it going to be essentially similar to other thermal energy plants that use water to capture heat and make steam and turn a turbine? Or is there a different way to capture the gamma rays that come out of this?
Well, so most of the energy in the DT fusion reaction that Alex mentioned earlier, 80% of it comes out in the form of neutrons, 14 what we call MEV neutrons, and then 20% comes out in the form of alpha particles, which are helium nuclei. And our trick is we assemble the conditions such that we can stop those alpha particles inside the fusion region, and that's how we get it to heat itself up. But the neutrons don't stop very effectively. They leave, especially for our case where the plasma is very small. So those neutrons fly outwards in all directions. And the idea for energy production, which we're not directly involved with at the moment, is that you'd have a blanket at large radius of lithium salt. And that lithium salt will react with the neutrons that hit it. And that does two things. You give up some of the energy of those neutrons, which cause the lithium salt to heat. And lithium also tends to create tritium when neutrons hit it. And then that tritium can be fed back in to make more of the nuclear fuel that's needed for the the fusion reaction itself. So once that lithium salt gets heated, just like you were saying, you carry that heat to a heat exchanger. You then make water hot and make steam, and you drive a steam generator. So at that level, it is very similar to the way we get electricity out of pretty much any thermal source.
Oh, that's interesting.
But the lithium salt does make it a little more complicated, yeah.
I think there's a lot of work being done in the fission community and the small modular reactors. On some people are looking at liquid salt coolant systems for fission reactions as well. So maybe the engineering would benefit from some synergy there. So very interesting to understand that. I didn't know that. That's cool to know. So you have you're being funded by the nuclear weapons. Is the goal of this work to actually look at the scientific aspects of nuclear weapons? Is that one of the goals of the work that's being done?
That's correct. We're funded directly by what's called the National Nuclear Security Agency, and they are the agency responsible for what we call the stewardship of the nuclear weapons. And like Alex was saying, they're the ones who pay for us and for our bills and for the experimental facility. And it is our primary mission to better understand the physics that's relevant to nuclear weapons. This was the vision back in the 1990s when nuclear testing ended, was that how do we know whether future generations of stockpile stewards kind of know their business, and how do we validate the computer models that we use to assess our nuclear weapons performance with in the absence of nuclear testing. So the idea is that the National Ignition Facility and a lot of the work we were doing becomes a surrogate for what used to be underground testing. And this is a way to basically kind of keep the competence level up of the people who are presently in charge of the nuclear deterrent. And, again, kind of assess our theoretical and computer modeling capabilities that we make decisions with.
So was this lab effort formed as a result of the test ban treaty or just following on? Was that like a direct?
It almost direct. I mean, our laboratory existed before the end of nuclear testing, and the laboratory that we're at, Livermore, is one of the two laboratories that designed quite a few of the nuclear weapons that were part of our deterrent and fought the Cold War with. But the development of the National Ignition Facility itself was kind of a direct offshoot of realizing that you need some sort of experimental training ground and a way to assess the science in the absence of nuclear testing that used to happen at the Nevada test site. So NIF is pretty much a direct result of the end of nuclear testing.
To be a little specific, I think the last nuclear test that the U.S. did was in 1992. And so you can imagine that people like myself were not doing a lot of physics in 1992, right? So,
so what is your mandate? Is any of your mandate towards energy, or is it mainly just scientific research, or do you have who sets your mandate, and how do you look at it?
Yeah, that's a great question. Our mandate comes from the National Nuclear Security Agency, and we are paid to do national security science. Now, pretty much all of us, like Alex and myself, who work on the National Ignition Facility, have interest in nuclear energy and fusion energy, but we are presently not paid to work on fusion energy. Now that we have achieved this step forward, it's starting to generate some interest in maybe funding us to do some more work that's directly related to fusion energy, but at the present moment we're not.
So there is actually an exercise underway now by another part of the Department of Energy that does have a fusion energy mission, where they're trying to review basically what the research needs would be for our type of fusion to try to put funding into pushing that forward.
Both Alex and I were just on a review panel for that, which is interesting. Yeah.
Nice. So that's a definite positive to get more work towards practical fusion energy. I'd like to understand a little bit about the relative strengths and weaknesses of the inertial confinement approach with respect to the tokamak approach, the magnetic confinement approach. Do you have like a pros and cons of one versus the other when you're looking towards practical fusion energy specifically?
Yeah. So Alex mentioned earlier this parameter that's a product of pressure, time, and temperature, which we call it's related to something we call the Lawson criteria. So for inertial confinement fusion, which is what we have been talking about, we have to create these enormous pressures because the thing only lasts for a very short amount of time. Magnetic fusion, the pressures that they have to achieve are much more modest, but they have to hold it for a longer amount of time. So the product of pressure, temperature, and time is about the same. So for inertial confinement fusion, just like you mentioned earlier, it's very impulsive. You have to keep dropping the target in and shooting it, creating these conditions, having it blow up, and you repeat that over and over again. And that's how you might envision a practical fusion power plant. Magnetic fusion is almost steady state. It's basically you set up the plasma. They generally focus on these devices called tokamaks, which are these donut-shaped magnetic bottles. The pressures inside that plasma are not super high. They're less than 10 atmospheres. 1 to 10 atmospheres. The temperatures that they try to achieve are within a factor of 2 of what we're trying to achieve. But because the pressures are so low, they basically have to hold on to it for a very long amount of time. The challenge for trying to hold on to a plasma for a very long amount of time are again, these instabilities where Mother Nature is trying to take the hot plasma and trade places with the cold plasma and take plasma that's at high density and trade places where it's at low density. And it's been an enormous challenge to try to confine the plasma the way you want it to get the fusion reaction to really take off. So that, in a way, both sides of inertial confinement and magnetic fusion both have to deal with instabilities. It's just on much different time scales. But magnetic fusion is quasi-steady state, where ours is impulsive. ICF is impulsive. Alex, did you want to add anything to that, or?
I would just say, as a general comment, I think anyone who's being honest with you ought to tell you that it's too early to say which is better or has better, easier engineering for a power plant. There's pros and cons, and we really just don't know. And I think, personally, I would say, sort of like when COVID started, right, and the government funded, several different approaches to make a vaccine because you don't know which one is going to be best in the end. Fusion is sort of similar. We just don't know which approach will be better. And so a diversified portfolio is kind of the way to go. And I would just emphasize too that, we're talking, of course, we're very excited about the progress that we've made, but the magnetic confinement fusion facility community has also made strides in the last few years and decade or so. So there's a lot of interesting results coming out there too. So I think we're kind of positive across the board.
Yeah, and this is interesting because I know, the media likes to blow things up and make a lot of excitement about this, and you see people on social media saying, "Oh my God, we're going to have fusion that's going to save us from the environmental crisis in 10 years." And some of us, who are maybe closer to the physics and understand the orders of magnitude involved in getting from ignition to total energy density positive is so what have we got? We've got 1% efficient, you said, in getting from the laser into the fuel, something like that. And then you have, your lasers are at most 10% efficient, and then you have to get back all of your initial investments and all of that hardware. We're 3 or 4 orders of magnitude out before we're commercial, right?
That's definitely true.
And yeah, again, I think it's sort of I don't know how to put it, but scientifically, I think it's actually, I don't want to say close, but this ignition threshold is sort of the last major scientific, new regime that we needed to get into. And from here, it's essentially just improving the efficiency, getting more of the fuel to burn and so on. But of course, that's very challenging. So like you say, to be concrete, the energy gain that we had on the record shot was about 0.72. So 72% of the laser energy came out as fusion. And for a reactor, for our approach, you need that to be something like 100. So that is still a long ways to go. But balancing that with the optimism of we have made a lot of scientific progress.
I was just going to say, we are transitioning from like a science focused project to engineering at this point, because it's really just a matter of kind of making things better now.
Yeah. Okay. How much? What's the theoretical peak efficiency that you can get out of this process? You're saying that 72 is what you got in this particular thing. Do you know how much you could get if everything was working well?
It was 72% is what we got from the present experiment. We should be able to get a factor of a few more on that using something very close to the present design if we can work out these issues. In principle, we should be able to get factors of 10 using the current facility that we have without a major revamp. But as Alex was just saying, we need like a factor of 100 for it to be practical, because you still have to overcome the energy consumed by the laser itself to make a practical fusion energy source.
And then once you get there, it's just engineering. Smooth sailing, right?
It's a difficult engineering. So I think it's unwise or overly optimistic to think there's going to be a solution in the next decade. So
it's still 20 years away.
Maybe 15.
Oh, well, that's good. I think it was 20 years away when I started my grad work, and here we are. But no, we are making progress, and that's good. But we need to understand that we still have a long ways to go to get this to reality, and we need to keep that in mind and temper our enthusiasm somewhat in the coming decade for fusion, because I know there are some people out there that have started up fusion companies as actual commercial efforts to make fusion energy, which I'm somewhat skeptical of. Do you guys have any insight into that? Have you seen these guys that are starting up fusion companies?
Yes.
Are you aware of any really good ideas out there that you think are innovative? And who's your money on?
I haven't invested in any of them, so I think there's I don't have a lot of money to invest either, but I think without naming names, I think there's a spectrum, right? I think there are some that are farther from the mainstream and some that are closer to the mainstream, and I think depending on your perspective, maybe you would weight one side of that higher than the other side. So
indeed. Well, I'm going to be trying to do a series of interviews, and I might see if I can get some of these people to come chat with me on the show and maybe explore a little bit about what they're doing and see if I can get some insight. So I'll report back and let you know what I find out. I'm sure I'm gonna try and get someone from the tokamak community to come on and discuss their work as well. What should I be asking these people? What you have any questions that you would ask what are you burning? What burning questions do you have?
So I think, just to kind of maybe point you in one direction on the magnetic fusion side, I think the company that's received the most funding by far is called Commonwealth Fusion. I think they just announced they have something like $2 billion in funding. There's other ones too that have raised large numbers of dollars, but not quite that much. And so I think, one thing that they would love to talk to you about, I'm sure, is their new magnet technology, which, like Omar was saying, the challenge on that is how long can you hold the plasma there? And so there's a lot of interest in kind of some of the new technology that they've been able to demonstrate. And then I think the other interesting question is always, what do you think will go wrong when you get into these new physics regimes, right? So, we've since we did the record breaking shot, we've had some challenges in being able to reproduce that, and we've learned a lot from that. Things are very sensitive in these regimes, so I think that's always a good question for anyone when say you build your new machine and you get into a new regime. What do you think is going to go wrong?
Always the case. Well, thank you so much for coming on the show and telling me all about your work. This has been really enlightening. I'm looking forward to more announcements coming out of your lab, and we get up to that 10 times threshold, and we can turn it over to the engineers, and you guys can go find new jobs, and we'll all be done. No, seriously, thank you so much for coming on and taking the time to chat with me today. I'm going to fire you off some Rational View t-shirts for spending your time and helping us to understand the work that's going on at LLNL on inertial confinement fusion, and hope that in 15 years we can go and christen our new nuclear fusion reactor. So thank you so much for coming on the show.
Well, thank you for inviting us.
Yeah, thank you for inviting us.
Okay, bye-bye.
If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/therationalview. Thanks for listening.